Okay, in this video we're going to take a look at our fourth and final perspective, which is going to be impulse and momentum. And so we're going to do the same thing like we did before with work and energy. I'm going to give you two lists just so you can see the direct correlation between what we've done before and what we're going to do now. So we have our translational equations, and then we have our rotational equations. The definitions in translation, we had impulse was equal to force times the time interval. So in rotation, we're going to say that the impulse, J, is equal to the rotational equivalent of force, which is torque, times the time interval. Then we have momentum was defined as mass times velocity. And so we use the letter capital L typically to represent angular momentum. And angular momentum is going to be equal to I times omega. And then we have our laws. Remember, these were definitions. And then we have our laws. We have, and theorems. So we have J is equal to delta P. That was the impulse momentum theorem. Well, now we're going to say J is equal to delta L. And finally, we have delta P was equal to 0. This was conservation of momentum. And we're going to have delta L is equal to 0. And this is conservation of angular momentum. And the last point I want to make is, remember that impulse, the concept behind it is that when we have an impulse, there is a transfer of momentum. And TRX is my shorthand for transfer. So let's take a look at angular momentum. Now, angular momentum comes in two varieties. The first type of angular momentum we can look at is something called spin angular momentum. Spin angular momentum is defined by L is equal to I omega. It is a constant in the universe. And all that means is that no matter where you go in the universe, you're going to have the same value for your angular momentum. And what makes it spin angular momentum is that the axis of rotation is through the center of mass. One of the most important features of spin angular momentum is that it's a stabilizer. Now, some common examples of things which are stabilized by spin angular momentum would include spinning a coin. All right, if you take a quarter or any coin and you flick it on its edge and you make it spin, it doesn't fall over. If you flick it so that it falls off of a tabletop while it's spinning, when it hits the ground, it still doesn't fall over, it stays upright. And the other example that you would be very familiar with is bicycle wheels. It's one of the reasons, not the only, but one of the reasons why you can stay upright on a moving bicycle. And the spin angular momentum points in the same direction as omega. Now, the second type of angular momentum that we can look at is orbital angular momentum. Orbital angular momentum is defined by MRV, and we're going to take a closer look at that a little bit later. Basically, we'll be looking at objects as point particles, and it's easy to visualize for the Earth what spin angular momentum is because we spin around on our axis in 24 hours, and then for orbital angular momentum, the Earth is effectively a point particle going around the Sun because we're so far away, and the angular momentum associated with that is something completely different. One of the key features for orbital angular momentum is that it is an arbitrary value. And again, we're going to look at this in more detail later. So basically, it's not constant in the universe. So as I said before, an object may have both types of angular momentum. The Earth was an example of that. So if this is the sun and the Earth is out here, then the Earth spins around on its axis in 24 hours, but it's also making an orbit around the sun, and there's an angular momentum associated with that. Now let's take a look at conservation of angular momentum. Okay, and in conservation of angular momentum, it's actually a little bit different from conservation of translational momentum, because in translation we always had two objects which were colliding. But with conservation of angular momentum, we actually have a situation where it can only be one object, and the momentum of that spinning object must be conserved. And the example of that is going to be whenever the object basically changes its moment of inertia. So I'll give you some examples here in a second, but I wanted to point out that it can be a single object. Now, if we have a single object scenario, then first of all, what we say, going back to basics, delta L of the system is equal to 0. And if we only have a single object, then we have basically L1 final minus L2 final, or initial, is equal, or L1 initial, sorry, is equal to 0. And when it's only a single object, we tend to drop the 1 as a subscript. But what we know is this: L initial is going to be equal to L final, even for the single object. So what's going to end up happening is this. You're going to have, maybe it's a large a large moment of inertia with a small angular velocity, but after the interaction occurs, in order for momentum to be conserved, you end up with a small moment of inertia and a large angular velocity. So some examples of this would include ice skaters. Okay, they start off and they have their arms out really wide whenever they're going to do a spin, and they pull their bodies in very, very tight, and when they do, they spin very, very fast. Divers, jumping off of a diving board, they do the same thing when they're doing their flips in the air, or even in acrobatics. When they're doing their flips in the air, if they need to rotate faster, they just get into a tighter tuck. And if they want to rotate slower, all they have to do is open up their body. And then we also have stars. Okay, the neutron star is a great example. And a neutron star is a star that started out its life as a normal size star, and then there's a gravitational collapse and the star shrinks down in size. As it burns out all of its fuel, it shrinks down in size. So you have a star that's going to, starts out as millions of miles in diameter, and then it turns out to end up being something that's only something like 10 kilometers in diameter. So it's very, very small, and they spin very, very fast. Some of these neutron stars can spin at over 1,000 revolutions per second. So a neutron star is a really great example of that. Just like before, if you have a multi-object interaction, then we still have delta L of the system is equal to 0. And then we get delta L1 plus delta L2 is equal to 0. So ultimately we get L1 plus L2 is equal to L1 prime plus L2 prime. And so this all looks very similar to what we've seen before. And I've got several demonstrations that we're going to do in class as it relates to conservation of angular momentum. So all I'm giving you here is the part which deals directly with the mathematics of it and how we set up our problems. So some examples of a multi-object interaction, that could be something like maybe you have a turntable and it's on a stand and it's spinning in this direction, and there's our axis of rotation. It's straight up, and you drop maybe a lump of putty onto the turntable, and that lump of putty it's going to hit, and this turntable is going to slow down as a result. Its rotation is going to slow down as a result. There's other examples where I'll have a couple of you sit in a chair that's easy to rotate, a low friction chair, and we'll put the spinning bicycle wheel in your hand, and I'm just going to have you flip the bicycle wheel over, and you start to rotate as a result. Okay, so that's basically it for conservation of angular momentum. Again, we're going to see some examples in class and in other videos.